Namaste from Brisbane in Australia. Greetings to all participants of the ISSRF-2022 meeting. My name is Rupert Ecker. I'm adjunct professor at Queensland University of Technology in Brisbane, as well as co-founder and CEO of TissueGnostics in Vienna, Austria. It's my great pleasure to present to you about contextual tissue cytometry with focus on reproductive health. This is a method for quantitative single-cell analysis in situ. What is tissue cytometry? I'm sure you are familiar with flow cytometry. Tissue cytometry brings the idea of flow cytometry to the slide and to the tissue section. It allows a functional single-cell analysis in the tissue section. It allows to look on multicellular structures like the tumor and cellular microenvironment and link it with single cells. It supports performing immunophenotyping, which means determination of the immune status in situ. Detection of multicellular structures like blood vessels, glomeruli, tumor area are possible. But we can also look inside single cells on subcellular compartments and structures like cytoskeletal elements or pathogens, bacteria, viruses, or intracellular parasites. Why is it important that we quantify? Well, let's make a step back and look at this in a broader sense. You may have heard of the reproducibility crisis. This term came around in 2016 when Nature published a survey among 1,500 scientists that revealed that 70% of researchers have problems in reproducing published data. And another 20% have even problems in reproducing their own data. So the question has been raised, do we have a reproducibility crisis and 90% of our data are questionable, if not wrong? So a call has been raised for a better mentorship. This is what each individual PI has to take care of for the students. A proper use of statistics. This is what each lab and the universities and research institutions have to take care of, and the more robust experimental design. This is where TissueGnostics comes in, and also my work at Queensland University of Technology. What is TissueGnostics? It's a company with its headquarters in Vienna, in Austria, in Europe, but we have a structure of globally active subsidiaries and offices on all continents. The company has been founded in 2003, so next year we will celebrate our 20th anniversary. As of end of 2021, we had more than 1,950 scientific publications from our clients in more than 60 countries on all continents. What I would like to mention is that TissueGnostics is not just a software company. We are an ISO certified manufacturer of medical devices. These medical devices are termed tissue fax. These are high-end microscopes from Carl Zeiss. TissueGnostics is OEM partner of Carl Zeiss, equipped with scanning stage for 8 slides or a slide loader for 120 slides, 1 or 2 cameras for color microscopy or fluorescence microscopy. And there are different versions to it, like we can add a spinning disc for whole slide confocal imaging, or work on an inverted system where also microwell plates can be analyzed, or live cell imaging can be performed. And there is a special configuration with a spectral camera that comes with a liquid crystal tunable filter for multispectral imaging. The immediate result of a TissueGnostics scanning is, like with any other slide scanner, a virtual slide, but at highest optical quality. Here we see an example of prostate cancer. In orange is the tumor marker, and we can literally see how the tumor invades the surrounding normal adjacent tissue. These are the individual prostatic glands. Like with Google Earth, we can navigate through our tissue and zoom in down to the cellular and even subcellular level, where we see here individual cells, nuclei with substructures, and cytoplasmic pattern. Why is quantitative analysis important? Let's look at this picture. We see here different frames with different shades of gray. Especially in fluorescence microscopy, intensities of molecules, intensities of stainings are recorded as gray values. Gray value 0 means black, gray value 255 means white. We have here frames with different shades of gray. Please look now on A and B and guess what's the difference in intensity. The human eye will not be able to see a difference of, say, 37 shades of gray, but I have prepared here some answers. What do you think is the difference between A and B? Which of these 5 answers is correct? I can tell you that the majority of people believe that 3 or 4 is the answer. In the next slide, we see A and B next to each other and might be surprised that there is in fact no difference. A and B are identical, although when we look at it, we see a difference. This appears, A appears darker than B, but when we compare A with A and A with B, there is no difference. This is in fact a phenomenon called optical illusion. The difference in intensity that we see between these two frames, in fact, comes from the environment, from the fact that A is surrounded by brighter areas, while B is surrounded by even darker areas. So the take-home message of this slide is that when we look at structures in a tissue environment, our perception may be determined not by the structure of interest, but by the environment. So there is a big difference between estimation and measurement. As we can see, the estimation would lead us here to a wrong conclusion. It would say A is darker than B, but in fact it's not. So it's important that we quantify our signals, our pattern that we observe in the microscope in an observer-independent manner. To do so, TissueGnostics has developed 3 software applications. They're called HistoQuest for single-cell analysis in bright field, TissueQuest for single-cell analysis in fluorescence, and StrataQuest for contextual tissue cytometry, both in fluorescence and immunohistochemistry, so transmission microscopy. A core element in TissueGnostics analysis is the quantification of the nucleus. And here we see also how we can quantify nuclear marker. This is an example of a column tissue in a standard immunohistochemistry staining with peroxidase in brown and the counterstain of hematoxylin in blue. So all the nuclei are blue and the marker in brown is Ki67, a proliferation marker. And the obvious question is how many cells are proliferating? In other words, how many of the blue nuclei are also stained in brown? And if you look at this picture, this image, please estimate, what do you think? How many cells are positive, brown positive in percent? We have made a survey among more than 200 scientists, and the answers that we received, believe it or not, ranged from 1 to 40%. So some researchers think that 1% of the cells are proliferating here, others think 40 or anywhere in between. And that's the important part. Whenever we do a visual evaluation, we get a range of estimations rather than a reproducible value. If we analyze exactly this sample in TissueFax, the algorithms will recognize the individual nuclei as indicated here by the yellow contours, and then measure for each nucleus how much brown and how much blue is available or is present. And this will be shown in such a scattergram, or people in flow cytometry will call it a dot plot. Each dot here represents a single cell in the tissue section. There is this important line called the cutoff, which is based on an isotype matched negative control. And what we get here is the positive population. And we see these are 14.5%. And the important thing is, whenever we do this analysis on Monday morning, on Wednesday noon, on Friday afternoon, in Brisbane, in Delhi, or in Vienna, we will always get the same result rather than a number. We can also apply this to markers which are expressed in the cytoplasm. We will also use the nucleus as a master channel, but then generate a secondary measure mask around each nucleus where we measure the cytoplasmic activity of a marker, as we can see here. This is an example from skin cancer. Here we see a biopsy of normal skin, where the marker is expressed at low level, and after UV irradiation, the marker expression increases in two ways. Then amount per cell increases, but also more cells become positive. Now, normally people will look at this and say this is 1+ positive and this is 2+ positive. And maybe your colleague thinks, no, this is, I would call it 3+. Rather than discussing how many pluses you assign, TissueFax gives you the observer independent quantification. Before UV, we have 16.7% of the cells being positive for this marker. After UV irradiation, this increases to 44.7. What we also see is this shift towards higher values, which means the increase in marker expression per cell. Here, before UV, it goes up to 90, after UV, up to 44. Sorry, up to 130 here. So this is the level of marker expression in the whole population that shifts towards higher values. One of the features that our clients around the world appreciate most is the ability to track individual cells between image and data space. So you can click on an image and it will start blinking in your scattergram, and you know exactly where the cell is located. So you have a link between a cellular phenotype and histology. Where in the tissue is this particular cell or cell population? Following our motto from image to data, we consider this a step forward and thus call it the forward connection. It also works the other way around, from the scattergram back to the image. We can make a gate, like in flow cytometry, a selection of a subpopulation, and the content of the gate will also be highlighted in a specific color, like here in red, in the image in the virtual slide. As a very nice feature that we have are the image diagrams, where we can show for each dot the corresponding event. So a crop of the cell, for example, or of the nucleus, rather than just a dot, as you can see here. A very important application is the phenotypic characterization of tissue infiltrating leukocytes, so determining the immune status in situ. You see here a 4-color staining with DAPI T helper cells in yellow, cytotoxic T cells in red, and FOXP3. Now you may know that CD4 and FOXP3 double positive cells are considered the regulatory T cells. So what we do again is that we use DAPI as a master channel. You see here in the green contours where the software has automatically identified the individual cells. And then we measure for each cell how much yellow, red, and green is there. And this gives us the output. We see here the CD4 positive population. Some of the cells, like this one, have a lot of yellow, so a high level of CD4. They will be somewhere up there. Other cells like this one are low level, so they will be closer to the cutoff, but still positive. But the rest of the cells here does not exhibit a specific staining of CD4, so they will be considered CD4 negative. The same we can do for CD8 and ultimately for CD4 FOXP3, so to determine the co-expression on single cell level. Here we see an example in prostate cancer. With the 4-color staining, we have in red the secretory epithelial cells, in yellow the basal epithelial cells, then the DAPI, and in white the tumor marker. What we see here on a normal area, there is this basal cell layer, and the secretory epithelial cells are negative for the tumor marker. But in the tumor marker, in the tumor area, the basal cell layer, the expression of this marker, it's called P16, gets lost, but the secretory epithelial cells express the tumor marker. And if we look here on the scattergrams, we see here the basal cell marker versus the tumor marker. In normal area, we have a clear population of basal epithelial cells, but no tumor marker. In the tumor, the basal epithelial cell marker disappears, and we get a prominent population of the tumor marker being present on the single cells. We are working under the umbrella of precision medicine, and it becomes more and more important that we are able to quantify more and more markers simultaneously on the same cell. Multispectral imaging is one approach to do this, where a liquid crystal tunable filter allows to acquire what is called a lambda stack. A lambda stack means that we acquire each fluorochrome several times, but at slightly different sections of the spectrum. So maybe shifted by 10 nanometer each. So for example, Alexa 488 gets analyzed by around 500, 510, 520, and 530 nanometer. From this spectral cube or lambda stack, we can then mathematically extract, by using reference spectra of the fluorochromes in use, how much of the total emission comes from fluorochrome 1, 2, 3, 4, 5, 6, 7, 8. As we can see here, this is a 5-color labeled mouse spleen. On the left-hand side, we see the raw data, overexpressed, spectrally overlapping, unspecific, but after unmixing, we get a very clear and highly specific staining. This has been used in a publication from MIT in 2020 to quantify the immune response against the SARS-CoV-2 virus in COVID-19 patients directly in the lung tissue, where the TissueFax, and in particular the TissueFax spectra system, was used to acquire and quantify 7 different markers on the single cells. I don't have the time to go into detail, but this paper was in fact the first indication that we have a problem with the corona pandemic, in that the SARS-CoV-2 virus tricks the immune system and avoids the formation of germinal centers, which means that long-term immunity is impaired. We are also working, in particular here at Queensland University of Technology, on AI-assisted methods. We have deep learning-based nuclear segmentation algorithm, which specifically is able to identify single nuclei in high-density areas like lymphatic tissue. This would be a classical nuclear segmentation, where we see there's a lot of issues here, wrong detection, while the nuclear segmentation based on deep learning gives a way better segmentation or recognition quality of individual cells. In this comparison, we see that the deep learning method is superior to classical image analysis. We're also offering solutions for machine learning-based classification of tissue structures, like we see here in a lymphatic tissue. we can determine individual classes that we're looking at. This can be done on the fly by the user. Then the training takes place, which takes typically minutes, and then it can be applied to the entire virtual slide. And here in the different colors, we see the different histological entities or classes in the tissue section. With this ability to determine multicellular structures, we can also identify like glands here, ducts, vessels, and combine with the single cell analysis. Let me show you also an example about ovarian tissue, where the aim was to look for primary, secondary, and tertiary follicles. The tertiary follicles are also called antral follicles. Here we see, for example, the primary follicle with a single layer of cuboidal cells. Here we have secondary follicles with multiple layers, and here we have tertiary or antral follicles with liquidity filled cavities. And our software was able to detect those types of follicles automatically, primary in blue, secondary in yellow, and tertiary or antral follicles in pink, in combination with single cell analysis. So you get a quantification based on an observer independent measurement. We have seen that we can look on single cells, identify single cells, the nucleus, the cytoplasm, subcellular structures, multicellular structures, and this helps us to do what is called contextual image cytometry. Here we see tumor area, where we can identify all the nuclei, as well as the tumor in orange, and then we can combine these measure masks and ask different questions, like in this case, how many CD4 positive cells are present, and where are these T lymphocytes, CD4? Are they inside the tumor or in the tumor stroma? And if they are in the stroma, how far are they away from the next tumor area? In this scattergram, we see the nuclei of the size of the nuclei, and only CD4 positive cells are shown. On the y-axis is the distance in micrometers. We can make gates here, which show cells, CD4 positive cells, in 1 to 25, 25 to 50, 50 to 100 micrometer distance from the next tumor area. And if we make this reverse gating or backward connection on like the first gate here, then we see in orange is the tumor, and in red are those CD4 positive lymphocytes, which are just outside the tumor, but not further away than 25 micrometer. And if we look on the quadrant statistic, it shows us that there is a total of 7,234 CD4 positive cells, and how many cells in total count as well as percentage are in which distance zone, distance in relation to the tumor area. And this we see here in the backward connection for the different distance zones. Always in red are the CD4 positive cells in a certain distance to the tumor. So what we get is a very detailed analysis, quantitative analysis on the single cell level. There have been publications in which the automated analysis has been compared to the gold standard, manual counting. The problem with manual counting is that when you have 3 observers who count how many cells are there, you get 3 results. The 3 results were taken, the median was calculated, and this was then compared to the software analysis, and we see that there is a very good correlation overall. With this, I would like to conclude my presentation. I hope I could show that with tissue flux cytometry, we can support researchers to move from image to data and thereby increase the observer independence and reproducibility. I invite you to take a look at our website, TissueGnostics.com, and there we will find a searchable database of reference papers. As I said, at the moment, or by the end of last year, there were 1,950 papers published, and you can search for certain markers, tissues, diseases, molecules that you're interested in, and see who has already published what using a TissueGnostics technology. I would also like to refer to this review article from my group, which was published last year, where we look on next generation digital histopathology of the tumor microenvironment, what is currently available. I would like to thank our collaborators from the European Marie Curie Innovative Training Networks, as well as partners from our collaborative projects with Queensland University of Technology. Finally, I would like to announce that next month, in March, a new dossier on artificial intelligence in biomedicine will be published. International researchers will provide a global outlook on AI in biomedicine. If you're interested to receive a PDF version or a reprint of this, please just drop me a message at r.ecker@qut.edu.au, and I will be happy to send you a reprint as soon as it becomes available. Danke, and enjoy the conference.